Hey, recorded, rolling. It is Wednesday, April 15. It's a record. Remind you guys about this elective sign up. So working on my side here. We got the senior takeover day, which is Friday, April 24th. I printed out a whole stack of these permission forms. So this is from admin, some idea. It says take the role of any faculty member. I don't know. Here, if that's something you're interested in, go ahead and pick up one of these and fill it out. If you wanted to teach physics that day, then let me know. It could be by yourself or with a group of friends. If you want to teach physics on April 24th, then I'll make a space where you could do something like that. Just let me know what's up. Okay, but main thing today is going to be this Play-Doh lab. Now, I did show you guys how to do this yesterday, so I'll show you guys real fast again today. Synopsis of what you're doing here. You guys have this lab table. Okay, and then remind you guys too, last few days we've been, going back to last week actually, I've been working on these pages. So there's this lab page. I had you guys set up different circuits with the Christmas lights and make some measurements and calculations, build some tables. Okay. I think almost everybody's turning this in by now. Turn in this lab. Okay. And then this page, which has some circuits on one side, and I think I covered most of these with you guys, okay, and left the rest of them for you guys. And I did do an example of each one of these on this side. Okay, so a lot of you guys have already turned this in, and if you haven't, then well, I'm starting to put those in the grade book. Also, actually got those. It's going to be a quiz on Friday. After you guys finish this lab, you'll have seen every question that's going to show up on the quiz on Friday. Yeah, so there's a quiz questions related to this lab today also. So I'll be there too. All right, so you guys go with what we're doing? Yes. Yeah.
There's a quiz today?
Friday. Okay. All right, so all right, what's going on here? So say same thing I said yesterday, but maybe a little faster. Remind you guys. So if you have okay, yeah, sorry, it's projected weird. If you have a wire, do you guys think that electricity through travels differently through a copper wire compared to aluminum wire? Yeah, I'm told copper is a little better, but maybe trade-off's a little more expensive, right? But it doesn't heat up as much. It's not as lossy. Right? So the property we're looking at, well, it's got to be some material property. Right? And that material property is called resistivity. And we're going to represent that with Greek letter rho. Now, in the past, like a few weeks ago, we used that letter to represent density, but in this context, it's resistivity. Okay? And how this formula goes like that, and then you could eventually create this looking graph that's the same thing as that formula, it's just the graphical version. So, guys, the longer the wire, because if you tripled the length of the wire, what would happen to the resistance from end to end?
3 pounds.
Yeah, it would also triple. Do you see triple? If the L triples, the R also triples. That's a direct relationship. What about this? What if you take this cross-sectional area? You guys see this cross-sectional area? Right? And what if you started off with a real skinny wire? And then you made this cross-sectional area bigger. So this A is getting really big now. Now what's happening to the resistance?
Smaller.
Yeah, it's getting smaller. It's getting less and less, decreasing. There's an inverse relationship. And what ties it together to make an exact formula is this resistivity value, which is some material property, like copper is different from aluminum, different from Play-Doh. Okay, and Play-Doh is we'll be looking at over here. Okay, so I got this Play-Doh. I'll give you guys each a canister of Play-Doh. Okay. And then we'll break out the batteries again. You can also use the cell phone charger. Now, the cell phone charger is only 5 volts. The battery should be 9, so it should be a bit better, right? Now, this first thing I'm going to do isn't actually part of the lab, but I just want to show you guys that you can bridge the gap with an LED. I think the long side's positive should go like this. Let's see if this turns on. There he goes. Oh, we got a blue one today. Right, you guys see that turned on right there? Right, so this Play-Doh is definitely transmitting some current, otherwise the LED would turn on. Right. By the way, if I reverse it, if I go back the other way, if I reverse the LED, does it turn on? No, because it only goes one way. So there it goes. Now it's back on again. Okay, so bridge that gap. I wonder if it works down here. Oh, actually, it does work. I should just put it down there to start with. So that turns on. You see, that's nice. Okay. This current has to travel all the way down here and then through the LED and then get that complete circuit. Okay, so let's get rid of the LED. Which you don't need. I might go into for fun. Okay? But we're going to create a circuit, something more like this. Okay? What's going on? Okay? Actually, you can use the diagram down here. And you can use the wires of the multimeter to hook this up, especially for the ammeter section. Right? So you guys have multimeter. Okay? And you guys have ruler. That's going to be a helpful tool today. Right? Or maybe I should go left to right. So we're building up to what is the resistivity of the Play-Doh. Right? What's the resistivity of the Play-Doh? So let's get this length, because that would matter. So I could measure the length that the current was traveling through. It might be like 10 or 20 centimeters, maybe something like that. I could measure, ooh, how about diameter? Could I do this to get the diameter? Maybe it might be like 2 centimeters or something. Okay. Uh, Now, guys, if you know the diameter of that cross section, could that cross section be estimated as a circular shape, pretty circular? Probably pretty close. Okay. Because if you know the diameter of a circle, how do you get the cross sectional area?
R squared.
Okay, so pi r squared. Yes, that's true.
Diameter.
True. Yeah. You could do that. Yeah, you could throw radius in here. That's true. Okay. I'm going to say this is equal to pi over 4 diameter squared. So in terms of diameter, it's pi over 4 diameter squared. So you can do that calculation. Okay. So I've got measure, calculate. Okay. All right, then break out the multimeter. All right, now the voltmeter section, you can switch this toggle switch to anywhere in the top left for volts DC. Okay. And remember, you're going to connect that in parallel with the Doh cylinder. All right, so exactly, just follow this picture right here. Okay. But then to measure, guys, what does I stand for in this class? Current. Okay. That should be in what unit?
Amperage.
Amps. Yeah. Okay. So voltage is in volts. These could be maybe ideally these could be in meters, okay, and this could be in square meters. Although this would be a tiny number for square meters, but good idea. Okay. And then, but you want to put the ammeter aspect in too. So you got to make some changes for ammeter. Okay. So remember, have this toggle have this lead plug in here for volts. I forgot I had that before. Okay. And switch this off. Then pull this out. Switch this over to the side that says amps, right? And then switch this to okay, something like that. So now you can measure current. Okay. But now the multimeter has to be in series with your circuit. You guys remember that? Showed you that yesterday, so that you can get a current reading. Now this is where this lab barely works because usually the current is very small and it'll just barely register on these voltmeters. Okay. Okay, so you get some everything. Hey guys, if you know voltage, you have a 9-volt battery, and you know current, how do you get resistance? Whose law? Ohm's law. You guys remember V equals IR? Could you use that to solve for R? V over I? Okay, and that's it. That would be in ohms, wouldn't it? Okay. I got an extra column in case you want to do an extra calculation. Might look like it's correct. Okay, and then resistivity. If you follow the units, it's going to be in ohm meters. Ohm meters. Okay. And then you guys see where it says make a graph right there? Okay. Well, you guys have a whole backside of this lab. So okay, go ahead, flip over and make this graph right here. You get, try different dimensions of this Doh cylinder. So let's go resistance and ohms versus length over area, and that would be in 1 over meters. Okay. Now I bet that you get points that line up in a straight line, and the slope of that line would represent the resistivity because resistance is equal to resistivity times L over A, just like I showed you on that PowerPoint slide that we just walked through. Okay. So basically that equation is going to be modeled in a graph. Okay. Okay. Can you guys scale these axes? I didn't scale the axes because I don't have any numbers, but once you get numbers on the table, say, okay, like my biggest resistance was so many ohms, and then put that here and then scale everything accordingly. You guys can do that? All right, so we get you all these materials, close up the squirting, and you guys got the rest of class to calculate resistivity.